So now we're going to talk about increasing and decreasing functions and the first derivative test. So we need to talk about what we mean by an increasing function. And here's the definition and a diagram. So a function f is said to be increasing on the interval I. We define what it means for a function to be increasing on an interval, not at a point. But a function is said to be increasing on the interval I if for every x1 and x2 in the interval I, with the x1 being the smaller one, in other words, x1 being the one on the left and the x2 being the one on the right, that we have f of x1 is less than f of x2. In other words, the y-coordinate on the left is going to be smaller than the y-coordinate on the right. That's what we mean by a function increasing on an interval. Now, if a function is decreasing, we have a similar definition. You can just change a couple of the words and symbols, and you've got the definition for decreasing functions. So the function f is said to be decreasing on the interval I if for every x1 and x2 in the interval I, with x1 on the left and x2 on the right, we have that f of x1, the y-coordinate on the left, is bigger than the y-coordinate on the right. So, can you find all intervals where the function is increasing and intervals where it is decreasing? And again, the squares here are marked off in increments of size 1. So this interval would be from, what would that be, -5 to -2? And that one looks, as we go from left to right, the y-coordinates are getting bigger, so it's increasing. And so that's what we do. We read this from left to right. And if the y-coordinates are getting bigger as we go from left to right, the function is increasing. If the y-coordinates are getting smaller, then the function is decreasing. So this next interval would be from 2 to 1, actually -2 to -1, and the function is decreasing. And the reason that I used the brackets here was that the points are included. And here I used the parentheses because the endpoints are not included. Now, what about from -1 to 1, I'm sorry, +1, 2, 3, 4, to 4? Well, the 1 is not included, but what about the 4? It is included. What if that graph had just stopped right there and we had a point? Well, you'd include the endpoint then. And then from 4 to 5, the function is decreasing. And again, don't be alarmed with the fact that we are including the 4 in both an increasing and a decreasing interval. We're not saying that the function is increasing or decreasing at that point. We don't even define what it means for a function to be increasing or decreasing at a point. I would say the function is not doing either one, but the idea is that if we pick 2 points in this interval, we can even pick this one, and it's still going to be bigger than any points to the left. Alright, so here's a theorem which I think will make a lot of sense. Let f be a function that is continuous on the closed interval from a to b and differentiable on the open interval from a to b. So it does not have to be differentiable on the endpoints. This may remind you of the conditions for Rolle's theorem and the mean value theorem. So if the derivative is positive for all x on that open interval, then f is increasing on the interval from the closed interval from a to b. So if the derivative is positive, that means we've got a positive slope. And so we've got something kind of like that, and the function is increasing. And as long as the function is defined at the endpoints, we can include the endpoints. Now, what if the derivative is negative? Well, then we've got something that looks more like that, and the function is decreasing. And what if the derivative is 0 all along that interval? Well, that means the slope is 0, and that means we have a constant function. So now we're ready to talk about the first derivative test for extrema. So we're going to start with a function with critical number c on the interval from a to b, and we need for f to be continuous and differentiable on that interval from a to b, except possibly at the critical number itself. At the critical number, you might have a cusp, and that's okay. You could even have you could even have a discontinuity as long as the point is as long as the function is defined at c. All right. So if f is decreasing on the interval from a to c and decreasing on c to b, then f has a relative minimum at the point c, f of c. So what's that saying? All right. Here's the number c, and here's the interval from a to b. If the function is increasing on this interval, sorry, that's exactly wrong. If the function is decreasing on this interval, and then increasing on this interval from c to b, so decreasing from a to c, and increasing from c to b, we've got a relative minimum at x equals c, y equals f of c. Right? Now, what I was trying to draw earlier is what goes on in situation number 2. If f is increasing on a to c, and decreasing on c to b, then f has a relative maximum at x equals c, y equals f of c. Remember, a relative maximum is like a hilltop, whereas a relative minimum is sort of a valley. And finally, 3 and 4 are very similar. If f is decreasing on a to c and decreasing on c to b, we have a situation where the function comes down. It might level off briefly at c, but then it's going to continue to decrease. There's neither a maximum nor a minimum at c, f of c. There's no extremum at all. And if f is increasing on the interval from a to c, and increasing on c to b, then there is no relative extremum here either. There's no hilltop, there's no valley, there's nothing. So we've discussed the idea behind the first derivative test for extrema. Basically what we're doing is looking to see whether the function is increasing, or where it's increasing, where it's decreasing, and then making judgments about extrema based on that information. But in practice, what is it we do? Well, the first thing we need to do is find all the critical numbers and discontinuities. Then we're going to need to find all the intervals that are defined by using those critical numbers and discontinuities as division points. I'll give you an example in just a moment. Then what we will do is select a test number, a test number from each of those intervals that we found in part 2. And what we're going to do is we're going to check the sign of the derivative at each of those test numbers. Those test numbers are the derivative at those test numbers is going to reflect whether the function is increasing or decreasing on the interval we're looking at. Then we're going to look for relative extreme according to the criteria that we talked about earlier. And there's this note. Remember that the first derivative test is for extrema is based on intervals, not on single points.